All right, welcome. In this video, we are going to discuss limiting and excess reactants. And a lot of times with chemical reactions, we use recipes as an analogy because they're really similar. So imagine you're trying to make a pizza and you've got a recipe for making a pizza. For every you need one crust, you need 5 ounces of sauce and 2 cups of cheese to make one pizza. You can see how we can write this out in something that looks a lot like a balanced chemical equation. So 1 crust plus 5 ounces sauce plus 2 cups cheese makes one pizza. You can think of a chemical equation as like a recipe to make a certain chemical, like a recipe for how to make ammonia or a recipe for how to make calcium carbonate. So this is a nice analogy when you're thinking about recipes. And when you're doing a reaction, just like when you're maybe cooking something in your kitchen, you don't always have the exact proportions of ingredients to work with. So there'll usually be some leftovers, and we call those leftovers the excess reactants. So let's look at this scenario. We've got a recipe here for making a pizza, and we look around the kitchen, we see that there's 4 pizza crusts, 10 cups of cheese, and 15 ounces of sauce. So you want to figure out how many pizzas we can make using this recipe. So one way you can think about this is you can imagine, well, what would happen if I used up all the crusts? So I have 4 crusts and I need 1 crust per pizza. So I have enough crusts to make 4 pizzas. Well, what if I used up all the cheese? I've got 10 cups of cheese. I need 2 cups per pizza. So I have enough cheese to make 5 pizzas. The sauce, I've got 15 ounces, but that's a 5-to-1 ratio. So I need 5 ounces per pizza. So I only have enough sauce to make 3 pizzas. So we say that the sauce is our limiting reactant. It's going to limit how much pizza we can make. And when I actually try and make the pizzas, I'm only going to be able to make 3 pizzas, because once I've made 3 pizzas, I will run out of sauce and I can't make any more pizzas, at least not using this recipe. Okay, so the limiting reactant determines how much product we can actually make. Here's another example. If I'm trying to make some hot dogs in a bun, I've got 5 hot dogs in my package. I only have 4 buns. I'm going to be able to make 4 hot dogs in a bun, and I will have 1 leftover hot dog. So sometimes we'll want to consider also like how much excess reactant is going to be left over when you're done making your product. Here's an example with this using a chemical reaction. So this is ammonia and oxygen gas combusting to make carbon dioxide and water. So you can think of this as a recipe for how to make CO2 and H2O. You can get it by combining 1 CH4 and 2 O2s. That'll make 1 CO2 and 2 H2Os. So let's say I have a reaction container where I mix together 5 moles of CH4 and 8 moles of O2. We want to know how much CO2 would I make from this combination. Okay, well, let's look at our CH4. It reacts in a 1-to-1 ratio. So every 1 CH4 makes 1 CO2. So I have enough CH4 to make 5 moles of CO2. I have enough oxygen to make 4 moles of CO2 because this reacts in a 2-to-1 ratio. So my oxygen ends up being my limiting reactant because it makes the least amount of product. So notice, in order to figure out which reactant is limiting, I don't want to just compare the starting amounts, right? I only need to compare how much product they could make. So even though we start out with more oxygen than than methane, because of this mole ratio, because we need 2 oxygens for every 1 CO2, my oxygen actually ends up being my limiting reactant. Okay, so the one that makes the least amount of product is going to be your limiting reactant. That's kind of the big takeaway here. So let's think about, here's some vocabulary. So we got a vocab page here. So limiting reactant is the reactant that's completely used up in the reaction. It limits the amount of product you make. The excess reactant is the one that's in excess. There's going to be some leftover. Theoretical yield is another term you might see. It's the amount of product that can be made based on the limiting reactant. So basically, it's what you calculate using stoichiometry. That is your theoretical yield. So like if we look back at this previous problem, we would say that our theoretical yield of CO2 is 4 moles of CO2. That's our theoretical yield. So it's the number that you calculate. As opposed to your actual yield. Actual yield would be if you went into the lab and actually did an experiment and collected the product and weighed it, and then that would be your actual yield. And we can calculate something called the percent yield by taking what you actually got in the experiment divided by what you theoretically should have gotten based on your stoichiometry. Okay, let's try some more with this limiting excess idea. So here, let's look at a sample problem here of how you might do this with a chemical reaction. So we've got the reaction between magnesium and oxygen gas to make magnesium oxide. So if we had 42.5 grams of magnesium and 33.8 grams of oxygen, what's our theoretical yield? So basically, how much MgO are we going to make? And who is the limiting reactant? So one thing you will notice, you can tell that something's a limiting and excess reactant problem when you're given amounts for more than one reactant. So notice how I'm given amounts for both magnesium and oxygen. So that's a clue that I'm going to need to apply my limiting reactant, problem solving process here. And how you'd solve this type of problem is you do two side-by-side stoichiometry problems and compare how much product each reactant could make if it were fully used up. And this is what we've just been doing in these examples. Do you see how we kind of did some side-by-side? We did two stoich problems and we compared whoever made the least amount of product. Same thing over here with the pizza. We did like 3 stoichiometry problems, and whoever made the least amount of product is my limiting reactant. Okay, so that's what we're going to do here. Okay. So whoever makes the smallest amount of product is known as the limiting reactant, and that will determine the theoretical yield. So how much product you actually expect to make, in the lab. So here's a visual showing this. See, we're kind of doing two side-by-side problems. You figure out which one makes less magnesium oxide, and then you can do this final step to figure out how many grams that would be. So here is, that setup here. So we want to say, starting with 42.5 grams of magnesium, how much MgO could we make if all that magnesium got used up? And then you do the same thing here, starting with the oxygen. So how much could we make if all that oxygen got used up? And this calculation gives us a smaller number of moles of product. Therefore, my magnesium is my limiting reactant. So this is how much I'm actually going to make in the reaction, is 1.7483 moles. Okay, and then I can do that final step and convert that into grams. All right, so let's try a practice problem here. So when you're going through these types of problems, it's helpful to take the time to figure out what is your known and what's your unknown. So it looks like right here, my unknown, the thing I'm trying to find is the volume of carbon dioxide. And then our knowns are, we know that we have 10 grams of baking soda, and then we know that we have 50 milliliters of 0.1 molar HCl. So this is our hint that this is a limiting excess reactant problem, because we know the amounts of both reactants and we're trying to find the amount of product. So if we're given two initial values of reactants, then it makes sense we need to do two stoichiometry problems. So we're going to set up two stoich problems. So the first one I'm going to set up starting with 10 grams of sodium bicarbonate, and I'm going to do some stoichiometry here. And I'm going to set up a second problem starting with 50 milliliters of HCl. So we're going to do two side-by-side stoich problems. And so this one, our first step in any stoich problem is to find moles. So in this case, I want to go from grams baking soda to moles baking soda. That relationship I find looking at the periodic table. So I see that 1 mole of baking soda weighs 84.0 grams. And then I want to find moles of CO2. So it looks like it's a 1-to-1 ratio. So this problem's a little easier because everything's a 1-to-1 ratio here. There we go. And so then I'm going to stop and plug that in my calculator. So 10 divided by 84. I've got 3 sig figs here. So I have enough baking soda to make 0.119 moles of CO2. And now we're going to do the same thing here with your hydrochloric acid. I want to convert liters of hydrochloric acid to moles of hydrochloric acid. So remember, when in doubt, find moles. That's always a good first step to do. And because it's 0.1 molar, that means there's 0.1 moles of HCl per every 1 liter of HCl. And then I want to go from moles of HCl to moles of CO2. So for every 1 HCl, I'm making 1 CO2. So it's just 0.05 times 0.1. So this is, I have enough HCl to make 0.005 moles of CO2. So this one is the smaller amount of product, right? So 0.005, right, is smaller than 0.119. So that means that HCl is our limiting reactant. And that means that this is how much moles of CO2 I'm going to make. So this is how much product I will get. Because once we made the 0.005 moles of CO2, you will run out of your acid. So the reaction is going to stop. So there you go. And the question asks me what the volume of this is. And this is a gas. So here's where I want to use PV equals nRT. Okay, so I'm going to rearrange this all for volume. So volume is nRT over P. And our N is our 0.050, right? Our pressure is 1 atmosphere. We'll leave R out for now. Our temperature, we want to make sure we convert it to Kelvin. Okay, so always have your temperature in Kelvin when you're doing gas calculations. And then if you look at your R value, you want to make sure you choose the R value that matches your pressure. So I want to use the one that is the, I'm running out of space here, 0.08206 liters atmospheric Kelvin mole. So use the one that is a atmosphere one. So then you got 0.005 times 0.08206 times, let's see, 294 divided by 1. So your answer here should be 0.12 liters. But I want that to be in milliliters. So we want to know this metric conversion. There's 1,000 milliliters per liter. So it's 120 milliliters. So that's a sample problem. And let me know what follow-up questions you have. Thanks for watching.